I mean, if he is in quarantine, what are you gonna do about it though, right?
He just said not going to be able to make it into class today.
Caught a case of the acute lazies, huh?
He's probably gonna blame me for giving it to him.
There's actually something else going on.
No,
Right now that is probably more suspect,
That's,
I
like I
get
said,
it.
it's fine.
Not an hour in.
You guys are adults, you guys can make adult
It was
decisions.
just a lot of fun.
All right, so we are here and we're making our way through chapters 7, 8, and 9. I think I've got just a small, little quiz for you guys for Monday there, just to kind of get used to doing things in an online format there, at least for this course. The thing to pay attention to is the last question on the quiz is going to ask you guys to upload your work. So kind of, one of my least favorite parts of having to do all this online stuff is just, you either get the question right or you don't, and how can I give partial credit? Well, the number's kind of close to what it should be, but as I've always stressed with you guys, I'm more interested in how you get to solve a problem, not necessarily just that you get the answer right. So just keep, just kind of like what you guys did for the exam there. The last question will just ask you guys to upload the work that you guys have for the the problems that need it, right? Obviously, I don't need to see your work for something like describe an energy transition or something like that. That's just you guys telling me what something means. Okay. But the instructions should be there, and if you guys do have any questions or run into any issues, let me know, because then as we move forward, that's kind of how we're going to be running the quizzes. Although with the exams, I'm still kind of thinking of what we need to do with that. All right. What's up? You have a question?
I worry.
Okay. Cool. So, I feel there was something else I was supposed to say. Anyway, must have not been that important, so we'll think of it as we go through that.
Okay, that's vaguely frightening.
Huh?
That's vaguely frightening.
What, did I forget things? I'm sorry.
No, it must not be important, but it might be.
Yeah, well, we'll figure it out, right? All right, so we were getting to the point where we start to draw our Lewis structures. And this is the way that we're going to represent how molecules look, how atoms are bonded together, how many bonds are in between atoms, where the lone pairs are, where the bonding pairs are. And we're going to use these Lewis structures to describe the properties of molecules, whether the molecules themselves are polar or nonpolar. Are they covalent? Are they ionic? How's their structure look? How do they talk to each other? All this kind of stuff, okay? So, on the upcoming exam or quiz, when I ask you guys, is this a polar molecule? Step 1 is going to be to draw the Lewis structure, okay? And then step 2 is to do the assessment to determine whether something's polar. And we'll walk through a couple examples of what I mean with that, right? But all I'm really saying is that drawing Lewis structures is an extremely important tool for us to have, okay? And I said that this slide here is going to be the steps that we take, right? And knowing the geometries up here is going to be super duper important also, okay? Because those are we're going to be, one of the questions is what geometry does this, molecule have, right? And the answers are only going to exist from that set there, right? There are no other geometries. So don't get creative, right? Unfortunately, I don't want you guys to get creative and come up with your own geometries. Well, I'm going to come up with something new. Well, sorry. Wait until you get your PhD, then you can do that, all right? For the moment, we're kind of limiting ourselves to those there. Yeah.
How do we know what geometry it has?
You're just supposed to know. I'm not going to give you any explanation about it, right? I'm not going to teach you anything about it. You just have to know. You're either born with it or you don't, right? Were you guys born with chemistry geometry?
No.
No, one person. All right, there you go. So everyone go and work with Michael, right? So, anyway, so we'll answer that question is what it comes down to. Yeah, don't worry. I'm not going to just throw you guys out into the deep end there, right? But the point that I did want to make with this, right, is make sure that you guys are following the steps. Okay, especially step number 4 there, when you guys are checking yourself on making that you have the correct Lewis structure or not. Okay. All right. So let's start working through an example here. So for this kind of stuff, you'll always need a periodic table around. typical question, right? I could say draw the structure of and give you the name of the molecule if I want to be particularly mean and nasty. I'm going to make you guys remember naming and then draw it, right? Or if I'm feeling nice and not too grumpy that day, then I give you guys a formula too, right? But make sure you guys don't forget your namings the other side of this, right? That's another big important topic that come out of the first semester of Jim Kennedy. So there we go, phosphorus trifluoride, PF3, okay? Step 1, we need our valence electrons, right? Valence electrons. So, where do we get information about that from?
We write out the configuration.
You don't necessarily have to, right? It'd be good to be good practice, kind of just to get used to doing your electron configuration, right? But we need our periodic table to get our valence electron counts.
Oh.
What group is phosphorus in? Group 15 or group 5, right? How many valence electrons does it have? 5. Where's fluorine?
7.
And your halogens, right? And halogens have 7, right?
Yeah.
So 5 from phosphorus, 3 times 7 from fluorine, right? So 21 there, 5 from there, total of 26. Okay, so here's a good point to always kind of stop and check our math. You're like, well, wait a minute, we barely did any math. So remember, okay, we're dealing with lone pairs. We're dealing with bonding pairs. We're dealing with pairs of electrons. So our total valence electron count should always be an even number. Got it? So if you get an odd number there, that means 2 things. One, you did something wrong, or you're dealing with one of these exceptions that are called radicals, which we'll deal with, okay? But it's always a good thing to kind of stop. 95% of the time, it should be an even number there, okay? All right, so 26 total electrons. That's step 1. Step 2, draw a skeletal structure, okay? Step 2 is draw a skeletal structure. Now, what we do in a skeletal structure, we typically put the least electronegative atom in the middle, okay? That's not always going to be the case, but that's a good place to start, right? Remember, I cannot give you the conditions for every single Lewis structure that exists in the entire universe. Why? Because there's billions of molecules. What I can give you is the way to start these, and then if we have to fix something, we'll catch it in step 4. Right, and then we have to go back and walk through some of these steps, okay? But I am giving you the method to get to mostly the correct answers, okay? In the least amount of steps. Excuse me, let me rephrase that. We're always going to get the correct answer. What I mean is we're usually going to get the correct answer on the first try with these steps is what it is. All right, so least electronegative goes in the middle. So let's take a quick pause here and switch over to our periodic table, okay? So remember, we're starting to do a lot of annotations on our periodic table. We number 1 through 8 across the top, and that helps us to tell how many valence electrons there are, okay? We number 1 through 7 along the left-hand side, and that helps us get the electron configurations, okay? Now we know our periodic trends about atomic radius, right? And ionization energy and electron affinity and all these kind of things that we talked about at the, in chapter 6. I forget now.
They all blend together.
Whatever the chapter was right before we started this. I forget what chapter we're on in here. I think it's chapter 7, right?
We're on 8.
Yeah, so it must be chapter 7, okay? So now one of these other very important trends or ideas to think about is electronegativity. Now in general, right, electronegativity follows the trend of electron affinity. But remember, right, what I said about electron affinity, and that is dealing with an atom in the gas phase. Right? Electronegativity deals when an atom is bonded in a molecule to something else. There is a distinction, it's important to recognize, but we can just kind of lump those 2 trends together also, right? That's mostly the way that it's taught, right? So electronegativity deals with this, all right? So let's do a mind exercise here real quick. So when an atom is bonded to another atom, okay? When an atom is bonded to another atom, there's going to be a tug of war, right? There's going to be a tug of war for those electrons pulling, there's going to be a tug of war for the atoms pulling electrons towards themselves, okay? So if I am an atom, and the more electronegative I am, that means I am better at pulling electrons towards myself. You guys with me on this? Okay. What makes an atom attractive to electrons? What do you mean?
Major electron cloud.
The size of the electron cloud, right?
Yeah.
So if I am good at,
Smaller atomic radius?
perfect, right? So the size of the atomic radius, okay? The smaller the radius of my atom means what? The closer those electrons are to the nucleus. What's attractive to electrons?
Protons?
The nucleus, the protons in the nucleus, got it? So the smaller the radius, the more electronegative the atoms are. Does that make sense? You see how everything kind of ties together with the radius here, right? So what does that mean? The smaller the radius, the more electronegative. What's one of our smallest atoms on here? Fluorine is, right? And in fact, fluorine is the most electronegative atom. Okay? Fluorine's the most electronegative atom. It's pretty much always going to win the tug of war. Got it? In fact, there's only one time it won't win the tug of war.
Special carbon.
Huh?
Or is it carbon or is it?
No, hydrogen's not that good at playing tug of war. It's only got one proton, right?
Helium?
No, helium doesn't want any.
Oxygen, maybe.
Hang on. Think, right? Let's instead of throwing out 92 other guesses, right? Let's think about this. Okay. So when would helium not be able to? When would fluorine not be able to pull electrons away from another atom?
It is fluorine.
Aha! You guys got it? Can you win against yourself? No. Right? It has an equal amount of, ability to play tug of war. So this is the thing, right? If you bond a fluorine to another fluorine, they're both playing tug of war, but which one's stronger? Neither. Got it? So when you're binding one atom to another, it's always a relative test of strength there. One of them is probably going to pull more than the other, unless it's bonded to itself. Then neither one of them will win. Okay? Does that make sense? Right? So fluorine is the most electronegative, and the general trend of things is that electronegativity increases the closer you get to fluorine. Okay? But you'll notice the trend is the exact same as for atomic radius, right? The smaller the radius, the more electronegative something is. Now, what I typically ask my students to do is to remember the top 4 electronegative atoms. That's going to be extremely important. Fluorine's number 1, oxygen's number 2. Oxygen is the second most electronegative atom, which means it will always win the tug of war, with 2 exceptions. When it's bound to fluorine and when it's bound to itself, right? Nitrogen's number 3. So fluorine's the most, oxygen the second, nitrogen the third, chlorine is the 4th.
Well, huh?
Now, a couple of thoughts that go along with electronegativity here. So electronegativity is not really something we can, let's say, measure, right? It's not like we can go measure this necessarily. It is, in ways, it's an arbitrary scale. But it's an arbitrary scale that we can observe, right? We can observe that in molecules, the electrons are hanging around fluorine more often than they are whatever it's bound to, okay? So we know it's something that exists, but, we can't really, put a number on it. But you're like, hey, wait a minute. I looked in the book, and there are numbers put on it. Yeah, there is a scale that's put with it. right? And fluorine is typically at like 3.9 or 4. But 4 what? 4 units of electronegativity. Okay, what does that mean? So anyway, there are numbers with this, and we'll talk a little bit about it and what that kind of is. The point that I'm trying to get to is that electronegativities is mostly a qualitative assessment. We look at atoms that are bound to each other and say which one's winning the tug of war. When one of the atoms wins the tug of war, okay? So if I'm fluorine, I'm winning the tug of war, I start to feel partially negative, okay? Because I have more electrons hanging around me. Got it? And if I'm feeling partially negative, then whatever I'm bound to has to be feeling partially positive. Now, how do magnets work? Well, there's negative ends and there's positive ends, right? And those negative and positive ends attract each other. It's the exact same idea here with molecules. When I have an electronegative atom, I generate these partial negatives and partial positives, and they can start to interact with each other, okay? And that's how molecules talk to each other. And so we'll get to that idea in just a minute. But electronegativity is very, very, very important. Got it?
Yep.
Got the idea for now? So fluorine the most, oxygen the second, nitrogen the third, chlorine the fourth. Okay? Now some books are going to say that I'm lying. Okay? I'm going to tell you that nitrogen's actually the fourth, and chlorine's the third. But I'm not. Okay, so there are disputes, is all we'll really say with this.
Why should we trust you?
Because I'm the one who controls your grade, so you better.
That's a great point.
Yeah, no, I'm just kidding. Right? No, it's a good question, right? Why should you trust me? Well, the answer is kind of goes back to the first point I made there. It's difficult to put a numeric value on these things. Right? So the real answer is in some situations nitrogen's more, in some situations chlorine's more, and so it ends up being a gray area, right? But for our sake, we'll just kind of stick with a definition, and we'll say fluorine number 1, oxygen 2, nitrogen 3, chlorine 4, and that will get you through life, okay? So that seems reasonable to me. What's up?
What's 5?
5?
Would it be carbon or bromine or silicon?
Yeah, good question. I don't know off the top of my head. I'd have to look it up. I just need to know the top 4, and that deals with most everything in life, right? And then I look at it on a case-by-case basis. What is bound together, and assess that, right?
So basically, it's the NBA finals of tug of warring atoms.
Sure. I don't know what the analogy you're making there.
My roommate turned 21 last night.
Aha. So late night partying. I see. All right.
More the substance involved in the party.
Yeah. Anyway, so important idea to start looking at electronegativity, okay? Now the first place we're going to apply this, that's not what I wanted. There it is, right? So the first place we're going to apply this idea of electronegativity is how we start to build our skeletal structure, right? We typically put the most electronegative atom in the middle. Got it? So if we're given a choice between phosphorus and fluorine, you guys should know now that fluorine is the most electronegative atom, which means what? It means that you're never going to see fluorine in the middle of a Lewis structure. Got it? Now the question might be why? Why do we say that the least electronegative goes into the middle? Well, we can think about it here in a minute. All right, we'll think about it here in a minute. Okay, so phosphorus in the middle. We put our fluorines around it. Is there a rhyme and the reason why I put the fluorines the way they are? Yes. Okay. And then to finish a skeletal structure, we connect our atoms to our central atom. I'm just going to make this look nice and pretty. Perfect. I've never seen a better drawn before. Okay. Got it? What did we do when we connect our atoms to our central atom? We made bonds, right? Bonds are made from electrons. So how many electrons have I used to make my skeletal structure?
6.
6. You guys with me on this? Right? Step 3, right? Let's switch to black here, right? Step 3 says, you add lone pairs to form octets, and you begin with the most electronegative atoms, or the ones on the outside, and work your way in. Okay? I started out with 26 electrons. I used 6 of them in my skeletal structure. So I got 20 left to deal with. Got it? So we start on the outside, work our way in. 2, 4, 6, 8, 10, 12, 16, 18. Okay? Why did I put that many electrons around my fluorines? Well, remember, what does it say in step 3 there? Use lone pairs to fill until an octet. Got it? Remember, these 2 electrons in red are being shared equally between the phosphorus and the fluorine. So the fluorine has access to those 2, plus 2, 4, 6 more, right? So 8 total electrons around the fluorine. Can fluorine violate the octet rule? No. Carbon, nitrogen, oxygen, fluorine will not violate the octet rule, ever. Ever, ever, ever. Well, that's not true. It will violate it when you guys put something wrong on the exam. So don't. Don't do that. Don't come up with new things that can't exist, all right? Does everyone catch me on how I filled in those lone pairs, though? Cool. So we still have 2 lone pairs left. Notice what's going on with our phosphorus there, right? Phosphorus has only access to 6, so we should give it our last 2 lone pairs here so it has access to 8. Good? Yeah.
Can you also just say like fluorine has 7 valence electrons and just like do it that way and like match them up? Or something?
Match what up?
Like, phosphorus has like 3 open sides, and then just like, and fluorine has 7, and then just do it that way instead of like counting them up and adding all the dots at the end.
You can,
Yeah.
but maybe I'd have to see exactly what you're trying to think of with that also. It sounds reasonable what you're saying, but maybe I'm just not quite putting it together there. Okay. All right, so then the most important step, step 4, okay? Step 4 says to check what we did. First part is to count our electrons. Did we add too many electrons accidentally? Right? Did we just go through and go crazy with how many electrons we added? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay? We didn't add any more electrons than we began with. Okay? We check our octets. Does anything have too many electrons? Doesn't look like we have in this case. Okay? And then step 3 is we check our formal charges. All right. So let's talk a little bit about formal charges. I believe there's some slides on this later. Okay. But formal charge is basically a way for us to track when things are not quite going as planned or not as expected. A formal charge is exactly what it sounds like. It's a formality. Okay? It is saying, in normal cases, I expect this atom to have this many bonds, or this atom to have access to this many electrons. There's something unusual going on in this case. That's what formal charge is. Okay? So formal charge is probably the most important check that you guys can do. All right? Because it's gonna throw up a red flag when you see a positive charge on an oxygen. And if you ever see a positive charge on oxygen, you should immediately go, right? There's something unusual going on here. There are cases where oxygen does end up with a positive formal charge, but it's just a formality. It doesn't mean that the oxygen's feeling positive. It just means that there's something unusual about how many bonds or electrons it has access to, okay? Because what do we know about oxygen? Well, it's the second most electronegative atom. Got it? So it's always going to be playing tug of war, and it's always going to be feeling negative. But when we assign it a positive formal charge, it should be a moment for you guys to say, wait a minute, I need to go check this to make sure I didn't make a mistake. Does that oxygen actually have that many bonds? Does that kind of make sense? Right? So it's an important assessment for us. It does help to define some of the positive and negative ends of a molecule. Okay? But there are some exceptions, as with everything in life. I think you guys are kind of starting to see these trends in chemistry, right? I'll teach you everything there is and I say, but wait, there's more, right? And I give you the exceptions. It's the same thing here with formal charges. Okay? Cool. So, hang on to this thought, leave yourself some space there if you're taking notes. We're going to come back and assign formal charges for these, okay? So I want to talk a little bit more about the how you calculate the formal charges. So leave yourself some space there. All right. So a little bit of practice here now. Phosphate, PO4, 3 minus. So see how far you guys can get without me rambling on here. As a quick this and that, when you're dealing with an anion, right, like we have here, that means you're going to add an electron for each charge that you have. Got it? So if you have a 3 minus charge, we have access to 3 more valence electrons. Okay?
For the whole molecule, right?
Or the whole molecule.
Okay.
Do what?
You said if you were to multiply like out the electrons, it's supposed to be an even number?
When you add them up, yeah.
Add them up, yeah.
Yes. Yep. Typically, you'll see an even number. You should be getting an even number here. No exceptions quite yet. Be careful, you're skipping a couple steps here. Don't add lone pairs on the middle until you add this up on the outside. This needs to be bonded to that central atom. So what you put phosphorus in the middle, put the oxygens around it, and connect the oxygens to the phosphorus with single bonds. So kind of like in a square, right? Really tough to draw. The mouse is very bad. All right. Looks like we're all getting there. Look over here. Good. So now start to fill in electrons from the outside. Working in. Right, so that's step 1, right? We got or where's your total valence electrons? So find how many valence electrons that has. Alright, you've got 4 oxygens, so how many each oxygen has? Then add 3 because of the 3 minus charge. Terrible. 32 minus 8 isn't 14. It's alright, I know it's early. Cool. So what was the dot method that you were trying to?
Well, cause if you start with, if you have phosphorus has like 5.
Yeah.
But then it's like, it doesn't work because then you try to like add bonds of,
Mm-hmm.
and then you run into like that.
Yeah, yeah,
So
yeah.
it doesn't.
It works, it's a good guess to see how many phosphorus typically wants.
Okay. But it's
Alright, because
not-
we know it says typically we will see phosphorus with 3 to complete
Yeah.
those there, right?
Yeah.
And that's kind of the happy spot for it.
Okay.
But like you're saying, they're like, wait a minute, right? Then we've got that lone pair there. Yeah. Alright. So let me see, what colors did I use for the other steps there? So green, red, black, and purple. Okay. So green. Right, calculate our total valence electrons. Phosphorus is 5. Right, 4 of my oxygens, that's 6 each. So 24. Right? So if we add that up, we see we just get to 29 electrons, and that should be a flag for you guys to say, hey, wait a minute, right? There's gotta be, I might be missing something here. So if you just add up the valence electrons from the atom, right, you'll get to 29, but we add 3 electrons from the 3 minus charge, right? So 32. Good? Cool, yeah.
Do you say there'll never be like a positive up there or something like that?
Sometimes there could be a positive, and then you take away a valence electron, right? So if I ask you guys to do the Lewis structure for ammonium, right, NH4 plus, you add up the stuff for the atoms, take away 1 valence electron. Okay? All right, so red, I believe, was the skeletal structure. Least electronegative atom in the middle. How do I know that phosphorus is less electronegative than oxygen?
Because oxygen's one of the big 4.
Okay, yeah, oxygen's one of the big 4, or you look at the periodic table, you follow the trend, okay? Is it important to start to be able to recognize which atoms are more electronegative?
Yes.
Yes. Okay, so just get in the habit of doing that, get in the habit of actively thinking about it, okay? We surround our we surround our phosphorus with our oxygens, and we connect everything with a single bond. Good? To do our skeletal structure, we have to use 8 electrons. Despite my cruddy handwriting, that's an 8, there it is, okay? So now we have to deal with, let's see, 32 minus 8, so what, 24, right? So 24 electrons that we have to use for step 3. Step 3 says what? Find the most electronegative, fill their octets, then work your way in. Got it? So 2, 4, 6, 8. Here. Okay. Good. Questions about this? Yeah.
Not necessarily about this specifically.
Yep.
But what if we get 2 atoms or elements and they're equally far away from phosphorus? How do we determine which one goes in the middle? Because they're both the same amount of electronegativity.
Yeah, good, that's a good question. So you're saying, your basic question is, what are you gonna do when I try to trick you guys, right?
I guess so.
I will never trick you guys in a way like that. I will ask you questions to make sure you're paying attention though, right? If there's some ambiguity about things like this, I will give you some information, is what it is. That's the best way I can answer it. Unless you have a specific example, then we can work through that one. But otherwise, I will say there will always be an obvious answer to it.
Okay.
Okay?
So, okay, sure.
Okay. The other way to think about it, usually the bigger atom goes in the middle too. Might be another way of looking at it.
Okay.
All right. So here we have our Lewis structure. Okay. Everything's looking good so far, but we're missing something, right? Do you guys see what we're missing?
We didn't check our work.
All right. We didn't check our work. Okay. What's the first thing we need to check? Did we use too many electrons?
Yeah.
Let's see, we've got 2468, 2468, 2468, right? So we got 4 groups of 8, that's 32. Everything good with that? Are we violating any octets?
No?
How many electrons does the phosphorus have access to? Let's see, 4 bonds with 2 electrons each, that's 8, right? Each oxygen has 8. Does everybody see that? That's important to recognize how to count those. Okay? So that's all good. So the last thing we should check is our formal charge again, right? So let's look at this one, because the idea is what? I told you guys that phosphate has a 3 minus charge. Do you guys see a minus charge anywhere? So we should probably put that down in there, right? Yeah.
So although it has access to 32 electrons, it doesn't actually have 32 electrons.
I see 32.
But isn't it like technically sharing them between phosphorus and oxygen? Like one here and then sharing one with phosphorus?
Yes.
So like,
But does that make it any less than 32? Just because they're sharing. 32 is just the total number. I didn't say anything about whether they're equally shared or unequally shared.
okay. Alright.
Okay. What's up?
So it has phosphorus has 5 electrons to start off with, right?
Yep.
Is the reason you have to like just automatically just connect your inner bonds, because if not, you would add the phosphorus electron first, so it like mess things up.
Ask your question one more time. I didn't quite catch.
Because so you have phosphorus, right? You know you told us to go all the way around and then make the second pair.
Yes, when you're doing the Lewis dot structure of just phosphorus. Yes.
Okay.
Yeah. So phosphorus on its own. And that's a useful way of looking at how many bonds phosphorus typically has. Because we have 3 unpaired electrons. And which means it'll typically see it with 3 bonds. And that's true. But as we can see here, that's not always the case, right? That's not always the case. So, if I tell you that something has a 3 minus charge, we should find where those minus charges are in the Lewis structure. That's where your formal charge comes in, okay? So, let's do that. If you peek ahead a couple slides, there's a formula that we'll get to, but I don't really like formulas, so I'm going to use magic science circles, okay? Now, magic science circle works like this. My magic science circle surrounds the atom that I want to get my formal charge for, okay? And my magic science circle cuts directly through every bond right in the middle of every bond that that atom is bonded to, okay? You guys with me? What I do then is I count how many electrons are in my magic science circle. There is 1 electron here. I cut this bond directly in half. That means only 1 of those electrons is in my circle. Good? 1, 2, 3, 4, 5, 6, 7. Okay?
Okay.
There are 7 electrons in my science circle. Oxygen starts with 6 valence electrons. Valence minus circle. 6 minus 7 gets me what?
-1.
-1. So my formal charge here is -1. Good? That's all there is to it.
But there's 4 oxygens.
Yes, there are 4 oxygens.
So,
Yes.
but I'm confused. Can you explain that whole like circle thing, like why you did that?
I did it I took the equation that they give in the book
Okay.
for calculating valence electrons, and I just made it in a visual representation.
Alright.
If you take, and I'll show you in just a second, part of the equation is they say cut everything in half. So I just say, here's a circle that cuts the bonds in half,
Okay.
right? So what my circle does is I'm looking at this atom, right? And I take 1 electron from each bond bonded to that atom. So I count 1 electron here, 2, 3, 4, 5, 6, 7, right? And that's my number here in blue. And then I just take my number in blue, and I need to know my valence electrons that I start out with. That's my number in green. So valence 6 minus the stuff in the circle 7 gets me my formal charge of -1. Okay? Cool.
So.
Go ahead.
Sorry. So you said we're taking the original valence of
Yes.
oxygen?
Yep.
Six,
The stuff that you get off the periodic table.
Okay,
Yep.
and then would it not always be 7 because of the octet rule?
No.
No?
Nope. Are you saying I'm wrong? Is that what you're trying to imply? It's a good question, right? And so we'll go back to one of the previous examples and we'll start to look at more formal chart. Right, but that's a good option. You're like, hey, wait a minute, isn't it always gonna be? The quick answer is no. Okay? What's
So,
up?
is the -1 charge gonna show up on 3 of the oxygens, but the 4th one is gonna be?
You guys tell me. Why don't you guys go through and assign your formal charges for all the other atoms in here? And then observe, right? So -1 formal charge on that oxygen. Right?
The circle goes through one of the bonds.
It cuts through every bond equally, right? It's basically just saying we count 1 electron for each. You guys don't have to draw this circle, right? You can just count 1 for each bond, but I'm a visual person. It's just easier for me to draw it than do it that way, right?
So the inter-bond from phosphorus to oxygen.
Yeah.
It's 1.
Yeah.
Right? But
Yeah.
then every other bond is like, it's still an actual like number, right? So. why
This is just a method for us to calculate something.
Okay,
It doesn't say anything about whether they're shared equally or not, or it doesn't change any of that. This is just a way to calculate something. It's a contrivance for us.
so because the phosphorus has a +1 formal charge, it cancels out one of the oxygen -1.
That's the way it works. What's up?
Okay, so where'd you get the 6 from?
6 is valence electrons
Oh,
from the periodic table.
okay.
Yep.
Okay.
I think I kind of did.
Good.
I hope it.
Right. So if we go through and do formal charge for all the oxygens, we'll see that they're all -1, right? Is that a coincidence, or is that a repeating pattern in this structure? We'll take a look at it, right? We have a single bond to an oxygen with 3 lone pairs. Okay? Single bond to an oxygen with 3 lone pairs. Single bond, 3 lone pairs. Got it? Every time you see an oxygen with 3 lone pairs and a single bond, it's going to have a -1 formal charge. Okay? Now, phosphorus in the middle. If we grab our science circle here again, right, we cut through all of those bonds. Okay? So we have 1, 2, 3, right? 4 bonds in the circle. Phosphorus starts out with 5 valence electrons, right? So a formal charge of +1. Good? So we have -4 from the total oxygens and +1 from the phosphorus. What is that up to? -3. Is that a coincidence, or is that how formal charges work? The answer is, that's how formal charges work, right? Your formal charges should add up to be your molecular charge. Got it? Cool. What's the oxidation state for everything in here? Ooh. Right? Pass. Right? But this is a question. Will you get is the oxidation state of oxygen in this molecule -1?
Yes.
No. Right?
2.
Yeah. So how could that be? Well, remember, oxidation state and formal charges and ionic charges, these are all different ways of tracking electrons. They all have a specific application at specific times. I'm not saying one negates the other. Okay, I'm saying both can be true, but they're telling us different information. Is it confusing to remember all those? Yeah. I mean, not for me. No, I'm joking, right? It is confusing to remember all those. Okay? I could still ask you guys the oxidation state for the oxygens in here. I'd expect you guys to be able to do that. Okay? But it gives us different information at different times. Formal charge is extremely important to help us tell things like polarity and did we draw the correct structure or not. Okay? Oxidation state is useful in things like what type of reaction occurred. Was it a redox? Was it precipitation? You know, all these different types of things. Okay? You guys following along with me? A little. Yeah, what's up?
So the formal charges and all those numbers, it's just a check of like our work. So it's not like anything you add to the structure or anything.
Good question, right? I expect you guys to tell me if I give you guys an ion, negative or positive, you need to put down the formal charges of where that negative and positive is on the molecule itself, right? Very, very good question. The only time you don't need to show me a formal charge is if the formal charge is equal to 0, right? If it's a neutral atom by formal charge, we don't care about that. Sound good? Cool. So let's back up then for just a second. Now knowing all that, tell me what the formal charges are here on PF3. Does that make sense? How do you know? The sum of the formal charges has to be equal to what?
0.
How do you know? The sum of the formal charges has to be equal to the molecular charge, right?
Right.
What's the molecular charge on PF3? 0. Got it. Good. You're lost. Well, we're in Florida. Right? A little place called Ave Maria. Middle of nowhere. Kind of boring. Right?
If you start flying south, you'll hit the Everglades.
So, we need to take a look at, so where's your PF, where's the drawing for that one, the other? No, the PF3. That's the previous problem we just did. Before, yeah, right, that's right, I see it through your paper.
Oh, that.
Yeah. So, do your science circle, right?
So we're on these, just these, right?
Mm-hmm. Make sure you got it, right? Perfect. Something goes over here. Okay. About that. Yep. I just count how many electrons are in this circle.
Oh, you're kidding me.
I mean, when you do a formal chart, you do it on any single one. You look at, this is that atom, that atom
Usually we
has
don't have
that
snow
formal charge.
Okay.
This atom would have that, right? It's a per atom basis. Okay.
Did you grow up in Texas?
I was looking back
Yeah,
here.
you're used to this.
0, does that make sense though?
Does it feel, it feels
Because PF3 itself is.
I know it sounds cliche, but like
Right?
if you
So all the formal charges have that.
like Halloween, but there's no.
Good.
I know, and it's like the kids don't
Go on.
have
I know. It's really nice though. Honestly,
Oh,
sometimes,
no,
sometimes like walking outside when it's cold.
How many rounds like those start out with?
Typically, the end of October, we get, like somewhere in late October, we get our first cold snap, and it'll start getting down. It's like the 70s during the day and like 60s at night.
The high will, the high
Sometimes
is
it
gonna
happens
remain
for Halloween, and it's so good for costumes.
It's gonna get down to like,
Yeah,
I'd still.
all right. Yeah. I thought I saw your hand go up. Okay.
Built a character. I know.
So just as a quick walkthrough, so we have 7 electrons, or each fluorine has 7 electrons, okay, in our science circle. But it starts out with 7 valence electrons, right? So green is valence, right? 7 is our circle. So 7 minus 7, 0, okay? So each fluorine has a 0 formal charge. I think so everyone get that the phosphorus has a 0 formal charge also, okay? Should you guys always get in the habit of doing your formal charges? Yes. Okay, I'm gonna ask you guys a question in just a minute. I'm gonna say, why is this not a good structure? And your answer is going to be based off of the formal charges, okay? Cool. All right.
So do we make our structures based off the formal charges?
No, we're following steps. Start at step 1, 2, 3, 4. If we find something odd in our formal charges, then we might have to go back and adjust what we did in steps 2 and 3. Okay? All right. See what you guys can come up with here, but be careful. One of the rules to pay attention to is that hydrogen will never be a central atom. You're never going to see hydrogen in the middle of something, okay? The notation? Oh, the bonding pairs. That's all it is, yeah. Yeah. But I don't see any formal charges, right?
I haven't done that.
Ah. Working on getting that PhD, kind of skipping steps already.
I just haven't done the shape right.
Well, the shape isn't right, but we haven't learned about why that is yet. You're fine though for what we're fine for what we know. That looks great.
Okay.
But the shape takes a little bit more work. Right. So we got 12 total electrons, 4 from our carbon, 2, 1 from each hydrogen, and 6 from our oxygen. Right? So we got a nice even number, so it looks like we can go and get started. So we put the oxygen in the middle, right? And we just put the hydrogens around the outside and the carbon over here, right? Is that how it goes?
For lines.
Oh, I need to connect them all with lines, of course, that's what I got wrong. Ah, perfect, right? What did I do wrong is what I'm trying to get you guys to see.
Oxygen more electronegative?
The oxygen's more electronegative, right? Don't put the electronegative atom in the middle unless there's a good reason for it, okay? No good reason here. Don't do that. There we go. All right. Cool. So now that we got that, there's our skeletal structure, okay? Our skeletal structure used 6 electrons. Oops, not the button. I'm not gonna do this. Our skeletal structure used 6 electrons, so we have 6 electrons left. So we start on the outside and work our way in, right? So here we go, 2, 4, 6. Yeah? Is that how it goes? No, that's not how it goes. What does that rule say? You start on the outside, beginning with what? The most electronegative atoms. Got it? So hydrogen certainly isn't more electronegative than oxygen is. Cool. All right, so we did steps 1 through 3. Step 4 says, check our electrons. 12, check our octets. What's the problem? Does oxygen have an octet? 2, 4, 6, 8, looks good. What about hydrogen? Hydrogen doesn't have an octet though, does it? So everything is wrong. World sucks. Okay, gotta start over. No, I'm just kidding, right? So hydrogen is one of our exceptions. Hydrogen is only ever going to have one bond to it. Ever. Ever, ever, ever. Ever, 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 ever. Even when you guys had me for organic chemistry, and you're like, I think he was lying to Gen Chem. I'm gonna put 3 bonds to it. Don't do it, okay? Don't. 1 bond to hydrogen. That might be an interesting thought to explain why hydrogen will only ever have 1 bond to it. So hydrogen only ever gonna have 1 bond. Okay, so we're okay with hydrogen. What's wrong with carbon? How many electrons does it currently have around it? 6. So we need to give it 2 more shared electrons. Oh, okay, that's easy. I can take care of that. There we go. Ah, perfect. Right? What did I do wrong?
Now we have 2 negative electrons.
No, that's okay, right? Electrons are always negative.
We had 0.
Don't add electrons, right? You can't create electrons out of nothing, okay? There's only one person who can do that, and he doesn't work here at the school, okay? Well, I hope he's at work here at the school, but I think you guys get the point, right? Okay? Don't just add lone pairs because you're like, well, I don't have an octet, right? Draw circles, then red pen comes out, and I get grumpy because it takes forever to grade your exam and all this, right? Don't, just get it right the first time, then you get 100. I get to go play video games and be happy, right? And you guys are happy too, right? So there we go, okay? Don't skip steps is what I'm really trying to get you guys to think about, okay? So how can I give electrons to something that's missing something? Well, what I'm going to do is take these lone pairs and share them in between the carbon and the oxygen.
Wow.
Okay? So I turn a lone pair into a double bond. Yeah.
I thought, didn't you say, or maybe you didn't, out of fluorine, oxygen, nitrogen, and carbon,
Yep.
is oxygen not more, is not, say was the least and the most? You said fluorine was the most.
Most what?
Electronegative.
Yeah, electronegative. And then, is it? any
Oxygen is
other-
number 2.
Carbon isn't
So,
in there,
oh, you put
fluorine
the
is.
least one inside the middle, right?
Correct.
Okay, the least.
Correct. Okay. So we got this. Everything's got an octet. We didn't add any electrons, so what's the last step to do? Check our formal charges, right? What's up?
Doesn't bother me, I just wanna know if there's a reason why you drew it like that.
Yeah, because that's the way that most of you guys drew it. It's not the real way it is.
Like,
But
why
we'll
would
correct that
hydrogen
just a
be
second.
over there, the lone pairs, I feel like the symmetry
They
of
will.
that, okay.
We'll get to that, right? We'll get to that. But be careful. I'll talk to you guys about the, I call them one of the logical fallacies in chemistry. And it's a fallacy that all humans succumb to, and that's the fallacy of symmetry. We have a proclivity to want things to be symmetric. Just because you want something, especially in chemistry, doesn't mean it happens. I think I told you guys on Monday or whenever it might be, I really want my reactions to work for my research. Doesn't mean they happen. Right? I wish they did, and I wish it'd be that easy, right? But so if you guys go through, see neutral formal charges for everything. Okay? Don't skip that step. Don't do it. Yeah, Dr. H, it takes like a half calorie to draw a circle and to add or subtract things. That's a lot of calories. Do it. Or don't, right? And then you're gonna miss things, okay? I don't want that to happen. All right, that seems like a good stopping point. We will pick this back up on a Monday there. Don't forget you guys have that quiz that's opening up. The quiz is on chapter 6 is what it is. So make sure you guys are studying through on chapter 6. And a little bit of chapter 7 might be in there also, right?
Thank you, Dr.
Hang on just a second. End this.